Look, if you're a technical project manager or system architect, you already know the drill. AI agents are incredibly easy to demo right now. It is easier than ever to build a slick, working prototype that actually completes meaningful tasks end-to-end. But taking that simple prototype and moving it to a robust, production-scale system, yeah, that changes absolutely everything. You might be sitting there thinking, well, why not just scale it up? Give it more steps, more tasks, less human supervision. But as we're going to see in this explainer today, scaling agents is nowhere near as simple as it sounds.
Today, we're charting a clear roadmap of the systemic principles underlying agentic architecture. We're going to start by breaking down the illusion of scaling, uncover the hidden single-agent bottleneck, watch some cascading errors in action, and then pivot right into solutions. The shift to multi-agent systems, navigating horizontal versus vertical capabilities, and finally, how to design for true system survival. Let's dive right in.
Okay, Section 1, the illusion of scaling.
There is a fundamental contrast here that we need to talk about. In traditional software systems, scaling is, well, it's a pretty well-understood problem. As demand grows, more users, more requests, you basically just add more infrastructure, right? You scale horizontally by tossing in more machines, or you scale vertically by cranking up CPU and memory. More users equals more infrastructure. But the system's underlying behavior, it stays the exact same. Agentic systems, though, completely break this pattern. Yes, of course they need infrastructure, but scaling agents really means expanding their actual capabilities so the system can do more. We're talking about making these AI systems work reliably across much wider scopes and vastly more complex tasks. It's a totally different ballgame.
To really understand why this capability scaling is so incredibly challenging, we have to look at the baseline. Most agents follow this fairly simple loop. They plan tasks out into steps. They execute those steps by using tools, they remember by storing relevant context to memory, and then they reflect to evaluate what actually worked. Now, for narrowly scoped tasks, this is brilliant. The problem is tightly bounded. The system makes a couple of decisions, completes the task, and stops. Your token usage is small, and the latency is barely even noticeable. But the second you expand into a new domain or bolt on a new suite of features, this whole loop begins to fracture.
Which brings us to Section 2, the single-agent bottleneck.
So the absolutely crucial point here is that while the core agent loop doesn't change, the cost of each execution absolutely does. As you scale up a single agent, latency and token usage metrics degrade non-linearly. Suddenly, planning takes much longer. Execution becomes widely demanding because the agent has to decide between a huge newly expanded pool of possible tools. Memory grows rapidly, which cranks up the context passed into every single step, basically forcing the model to fight through a ton of noise. In reflection, it becomes crazy expensive and way less reliable because all that massive context just dilutes the useful signals. To calculate the real financial impact of this, you absolutely cannot just look at base token prices. You've got to track the token per step growth multiplier and factor in the compounding cost of error retry loops. What used to be a really quick, cheap interaction suddenly multiplies the complexity of every single decision. The financial hit here isn't just a slight bump, we are talking about a non-linear spike in the cost per decision and ultimately the cost per successful outcome.
This quote really hits the nail on the head regarding the core issue, which is ownership. Think about it like a CEO bottleneck. Imagine a startup where every single decision, engineering, marketing, hiring, customer support, literally all of it has to go through one person. As that company grows, even the simplest decisions just grind to a total halt because the CEO has to absorb way too much context and constantly switch between specialized domains. Well, agents operate the exact same way. When responsibility is highly centralized, it's not some underlying model limitation you're hitting, it's a systems design problem. The real bottleneck is the rapidly growing cost of making each centralized decision.
Let's look at Section 3, Cascading Errors in Action.
Let's walk through a real-world timeline to see how this plays out. Say you ask a single-agent system to book me a trip to Washington. At minute 1, the agent starts planning, but it misinterprets Washington as Washington, D.C., when you actually meant Washington State, which is, nearly 3,000 miles away. By minute 2, it executes its tools to find flights to D.C. By minute 3, it's booking D.C. hotels and organizing ground transport. Now, all of these steps execute successfully from the agent's point of view. But by minute 4, that initial false assumption has driven the entire plan, completely influenced the execution, and is now permanently written into its memory. In just 4 minutes, the system has flawlessly orchestrated a completely ruined vacation. The memory is officially poisoned for all future actions.
This right here is the key shift you've got to understand. Failures are not isolated, they propagate. The system didn't just make a tiny, harmless hallucination, it spread that mistake across time autonomously, wasting resources along the way. And because the system is operating autonomously on your behalf, there usually isn't a natural checkpoint where a user can just step in and easily correct it. As agents scale, they're actually making more decisions under uncertainty, not less.
Which leads us to arguably the most important question for any system architect today. If centralized single agents become way too expensive, way too slow, and highly prone to these catastrophic cascading failures, so what do we actually do about this?
That brings us to Section 4, the shift to multi-agent systems.
The answer is decomposing the system. By breaking it down into multiple components with bounded and distributed responsibility, we basically regain control. Each component operates with far less context. It makes fewer decisions, and it has a dramatically narrower scope. By distributing the work like this, individual decisions suddenly become cheaper, they become faster, and they're much easier to reason about. But the absolute best part? If an error happens, the complexity and the failures are contained entirely within that specific boundary, rather than compounding like wildfire across your entire system.
Moving on to Section 5, horizontal versus vertical capabilities.
Technical project managers definitely take note of this one. As your system evolves, you basically have two main paths. The first is horizontal coordination. This is where you introduce entirely new agents to take on distinct responsibilities. Now, this is fantastic for reusing capabilities, but the trade-off is high communication overhead. Coordination essentially becomes your limiting factor. The second path is vertical expansion. Here, you increase the capability of individual agents by giving them more internal tools or subagents. This definitely reduces coordination overhead, but you're trading that for higher latency and higher complexity concentrated right back inside that specific agent.
Let's look at a really practical example of capability placement within, say, a research assistant system. Suppose you want to add fact-checking to this system. The best move is to make it a separate agent. Why? Because fact-checking is a reusable, independent capability with its own specific logic. It keeps responsibilities totally clear, even if it adds a slight coordination step. But what if you want to rank and filter search results? Well, you should actually embed that directly into your existing retrieval agent. It's tightly coupled to the retrieval process and relies heavily on shared context. Splitting that off into its own agent would just fragment the decision process and create totally unnecessary coordination.
So here is your executive takeaway. If you need a definitive rule of thumb for your next build, it's this. Split capabilities into new agents when they are reusable and independent. Embed capabilities when they are tightly coupled and context-dependent. Systems that actually scale successfully in the real world are built by teams that perfectly balance these forces, deliberately choosing exactly where complexity is allowed to accumulate.
Finally, Section 6, designing for system survival.
The harsh reality of agentic AI is that scaling doesn't just amplify capability, it amplifies absolutely every single system constraint simultaneously. Costs rise rapidly, latency increases across every single step, failures propagate silently if they aren't contained, and coordination overhead absolutely spikes. At every stage, scaling introduces a new constraint. The teams that are going to succeed in this space won't just be the ones using the most capable foundational models. No. They'll be the ones who deeply understand how decisions flow through their architecture and who make deliberate, calculated choices about what is allowed to scale and what absolutely must be kept bounded.
Once you fully understand these mechanics, you can start actively shaping how decisions behave at scale in your own products. So I'll leave you with this one thought to chew on for your own projects. Are you designing systems where intelligence compounds? Or are you building fragile structures where it's just going to collapse under its own weight?